A closed-loop control system for position control is comprised of proportional, integral, and derivative circuits, and is often referred to as a PID. The operation of PID mode control is demonstrated in the following robot arm position circuit. To move the robotic arm to a specific position, a command signal from the computer starts the motion sequence. The analog command signal voltage produced by the digital to analog converter determines the position of the arm. The potentiometer attached to a robotic arm in the circuit indicates the actual position. The variable voltage produced is referred to as the feedback signal. When the feedback signal voltage matches the command signal voltage, the arm has reached the desired position. For example, with the arm at the bottle pick position, the potentiometer output voltage of 0 matches the command signal of 0 from the computer. To change the arm to another position, a command signal from the computer is required. The command signal from the computer consists of binary numbers that increment until a value is reached that represents the desired position. The binary value is then converted to an analog voltage by the digital to analog converter that indicates the position that the arm is required to move. In this system, there is not an immediate response by the robotic arm and the command signal. The delay of the arm and feedback signal creates a positive error signal voltage at the output of the difference op-amp. The error signal is inverted by the proportional difference op-amp to a negative voltage. The voltage is then amplified by the power amp and inverted to a positive voltage and applied to the motor of the robotic arm. The robotic arm moves to the desired position until the error signal at the difference op-amp is 0. When the arm reaches the desired position, the difference op-amp voltage is reduced to 0, and the feedback voltage from the potentiometer equals the command voltage of the computer. To increase the response time of the robotic arm to the command signal, the gain of the proportional amplifier can be increased. Increasing the gain of the op-amp has a disadvantage where the robotic arm overshoots the targeted position. When this occurs, the feedback signal is greater than the command signal. The op-amp reacts to this condition by changing the polarity from positive to negative, which results in reverse rotation of the arm motor to go back to the desired position. Although with high gain, the overshoot is repeated again in the opposite direction. The overshoot of the target position repeats until the robotic arm motor stabilizes. To achieve a fast response time and minimize overshoot of the desired position, a derivative amplifier is added to the circuit. The derivative amplifier produces an output while the signal applied to the amplifier's input is changing. As the arm lags behind the command signal, the error signal generated causes the derivative amplifier to produce a voltage that adds to the output of the proportional amplifier. The sum of both voltages is applied to the power amp, which results in the robotic arm to accelerate at a similar rate of the changing command signal. The error becomes constant when the voltage from the potentiometer indicates that the robotic's arm position is changing at a constant rate of the command signal. At this time, the derivative voltage changes to 0 volts, and the proportional amplifier continues to produce a voltage. As the command signal stops changing, the robotic arm continues to move with a decreasing error signal. As the error is reduced, the derivative amplifier output voltage changes polarity and cancels the proportional voltage. If the error signal decreases too fast, the derivative voltage will be greater than the proportional voltage. When this occurs, the polarity of the power amp is reversed, creating a brake condition to prevent overshooting the desired position. As the arm continues in motion, the feedback voltage is nearing the command voltage. The error signal from the difference op amp is also decreasing, and as a result, the arm motor speed decreases. Friction and mass of the robotic arm contribute to the system negatively, where the robotic arm fails to reach the desired position. With a reduced error signal due to feedback voltage and command voltage not being equal, a steady-state error condition exists. In this condition, the difference op amp creates a steady voltage, and the arm continues to move. To overcome the steady-state error, an integral amplifier is added to the circuit. With an error signal of 0, the output voltage of the integral amplifier is 0. The integral amplifier increases gain depending on the duration of the error signal. For example, the longer the error is present, the larger the amplifier gain. The output of the integral amplifier increases and is further amplified by the power amp to overcome the friction and mass of the robotic arm and completes the final move to the desired position. The feedback signal is now equal to the command signal. Output voltages of the amplifiers are 0, and the robotic arm motor stops turning.